morning. So today we have Professor Fortney from Cruz in the senior seminar. So Jonathan is PhD from University of Arizona, and then he was at NASA Ames for a few years before joining UC Cruz as a faculty. And he's now also the director of this Other Worlds Laboratory, which has a very nice logo. And today he's going to tell us about the beauty of giant planets. Welcome.
All right. It's great to be here. I was last in town about 3.5 years ago for the Center for Planetary Sciences. It was my first visit to CITA in particular, so it's good to be here. So my talk today is thinking to some degree about lessons that we've learned about Jupiter and Saturn and looking at a much larger population size for exoplanets. Which of these lessons in terms of how Jupiter and Saturn formed or in terms of their composition today are things that we see borne out in the much larger giant planet population that we get from transiting planets. So it's an exciting time to be studying planetary physics in that we're going from obviously a much smaller sample size to a much larger sample size, and that's only just going to grow as time goes on. So it's also a great time because, as I mentioned, we're in a position now where we can think about planets as a class of astrophysical objects. Also, Juno at Jupiter and Cassini at Saturn are giving us very detailed ground truth knowledge of those planets in a way that's essentially unprecedented in terms of their structure and composition. A result from NASA's Juno mission over the past couple months was that the visible banded structure that we see in Jupiter goes down about 3,000 kilometers. So it's relatively deep. It's not just a surface phenomenon, but it's not something that goes all the way down to the core. And that's something that we could tell from Jupiter's gravity field. And some similar results will be coming out about Saturn in the next, I think, sometime this summer from the Cassini grand finale. And so with exoplanets, of course, we have a much larger sample size, so we can actually ask and answer different questions than we can in the solar system. There's, of course, questions we'll never be able to ask in terms of data quality, but we can ask and answer other questions given our larger sample size. So just so everyone's on the same page, I want to talk about some details of interior structure of Jupiter and Saturn, because they're going to be kind of our analogs. Their visible atmospheres are enhanced in metals compared to the sun. So Jupiter and Saturn, although they're mostly hydrogen and helium, they don't have the same composition as the sun. The Galileo entry probe dove into Jupiter's atmosphere in 1995 and showed that it's about 3 times solar in a variety of elements compared to the sun. That's just direct observation. We think the planet is mostly or fully convective, such that that's the expectation for the metallicity enhancement of the whole hydrogen-helium envelope. There's also a core of something like 5 to 15 Earth masses. This changes around a little bit over time, but it's something on that order. For Saturn, its visible atmosphere, there's no entry probe, but from spectra we can tell it's something, 4 is a little low now, I should update this, something on the order of 7 to 10 times solar. And Saturn has a core of around 10 to 20 Earth masses. So thinking about them in this helium business is a whole story for another day. We won't get into that today. But the surfaces, visible surfaces we see are relatively cold. The deep interior is quite a bit hotter, and they're mostly made of liquid metallic hydrogen, which is a sea of protons and electrons. Both planets have a dynamo in this region that generates their strong magnetic field. But on the whole, thinking about metals or heavy elements, Jupiter's about 5 to 10% metals, whereas the sun's about 1.5%. This number is stabilized recently over the past couple decades. It kind of went up and down for those who follow the sun. Whereas Saturn's about 15 to 25% metals by mass. So they're strongly enriched compared to the sun. Uranus and Neptune are actually whole different beasts. They're mostly made of water and rock. They're mostly metals, with only about 10 to 20% of their mass being the hydrogen-helium envelope. So what we've learned about giant planet composition is that as you go to smaller giant planets, their metallicity enhancement increases, but that's a sample size of 4. And we'd like to look in the extrasolar planetary regime to see how these trends are borne out in a much larger sample size. So the way we understand this is through the core accretion formation scenario. There's been a variety of papers on this over the past 30 years. This is in some sense, the very first very modern calculation from Pollock et al. In '96. This paper came out at around the same time hot Jupiters were discovered. And this is actually the most cited paper in the history of the journal Icarus, at something like 2,000 citations. And the basic, and this was also pioneered by Peter Bodenheimer, who's at Santa Cruz. When he retired, I actually got his slot, so I feel very warm and fuzzy about that. I see Peter a lot. He still comes into work pretty much every day. So the basic idea is that you form, this is mass in Earth masses. This is time in millions of years. These are just two different scenarios with a faster accretion time and a slower. But the basic idea is that you build up a core first of around 10 Earth masses. And that core then slowly accumulates some amount of hydrogen and helium. And eventually you reach a crossover point where you start to accrete tremendous amounts of hydrogen and helium. And it's not quite that well understood how this tapers off. But basically you end up with an object that accretes metal in the core. Then you also accrete additional metal over time. Hence the name of the paper, Concurrent Accretion of Solids and Gas. And so you end up with an object that's metal enriched compared to the parent star, both because of the formation of the core, but also the additional accretion of metals while you're accreting the hydrogen and helium envelope. A lot of these details are not that well understood. This is a one-dimensional model of a three-dimensional formation scenario. This is the general framework we have to understand why planets are probably metal enriched compared to their parent stars. What we'd like to do is quantify this a bit more in terms of the planets we see today. So I think a lot of you already know about exoplanets to a large degree, so I'll skip through this pretty quickly. But typically, lots of plots like this get shown where you're looking at orbital separation in AU versus planet mass in Jupiter masses. There's the hot Jupiters over here. There's the huge array of Neptunes and sub-Neptunes and super-Earths down here that Kepler's found. These can be found by radial velocity, transits, direct imaging, microlensing planets. We're a pretty expert audience, so we know how radial velocity works via the Doppler shift of the parent star's light. Transits involve blocking out the parent star. You can measure the planet's radius. And imaging, which I'm not going to talk about today, gets you great pictures of planets at larger orbital separations. What I want to talk about, and so when people talk about planet formation, they often want to compare a planet formation scenario to a diagram like this. What are the masses of the planets, and where are they? In the solar system, that's been useful, but also thinking in more detail about the composition of the planets itself has also led us to real gains in understanding planet formation. So one of the aims of my work over the past few years has been trying to think about this in a third axis of composition. So taking a diagram like this where we have planet mass versus some major axis, but also thinking about the composition of those planets themselves. Be it for transiting planets, we can get the mass and the radius. That tells us something about the planet's density, which tells us about its composition. You can also perhaps measure the atmospheric abundances of planets to tell us about composition. And we can compare that to the parent star abundances to look for similarities or differences between planetary composition and stellar composition. And so in terms of where we are now, there's about on the order of 300 gas giants. So things are, let's say, about 15 to 20 Earth masses or larger that have a well-determined mass and radius. And the mass and radius gives us the density, which tells us something about its composition when you compare to a model. Of course, these methods, as illustrated here and here, both have a strong bias towards finding relatively large planets on relatively short period orbits. They'll give a stronger radial velocity signal. They'll have a deeper transit. So NASA's Kepler mission found about 5,000 transiting planet candidates, but nearly all of them don't have a mass constraint. So here we'll be focusing on objects that do have a good mass constraint. And the gas giants are the population where they're inherently not as common, but they're the sample size that we have the best data for in terms of their mass, radius, and density. And so we can, on a simple diagram like this, we can start to build up some intuition about planetary composition in terms of density. So this is radius in Earth radii. This is radius in Jupiter radii. They differ by a factor of about 11. This is mass in Earth masses. This is mass in Jupiter masses. They differ by about a factor of 300. This plot's a few years out of date, but if you make a model planet that's pure iron, pure rock, or pure water, these would sit down here. So Uranus and Neptune sit above the pure water curve. They have a larger radius and a lower density than a pure water planet. So in addition to being able to look at the planet and seeing it has a hydrogen-helium envelope, you know just from its mass and radius that it has to have hydrogen and helium because it sits above this curve. Earth and Venus down here are about 2/3 rock, 1/3 iron. So they sit closer to the rock curve than the iron curve. So it's a very simple way to think about their composition. Jupiter and Saturn sit over here. They have a mass that differs by a factor of 3, but a radius that only differs by about 15%. And one of the things that's been really surprising over the past 15, 20 years is that the transiting gas giants can have masses that are the same, but radii that differ by about a factor of 2. And so we've been trying to understand why that might be based on their formation and evolution, how they can end up with such different densities and radii. You can just overlay curves of constant density on here. This is 0.1 gram per cubic centimeter, 1, 10. You can see there are gas giants that have densities similar to styrofoam, about 0.1 gram per cubic centimeter. Hydrogen's an extremely compressible material. As you add more and more and more hydrogen, many orders of magnitude more hydrogen, the radius stays very similar. This is, and the n equals 1 polytrope is very similar to this, where you get a flat mass radius curve. And these, of course, these fall down a bit as you get to brown dwarfs, and the white dwarf side of the curve would be way over here. And so they have radii that don't change a whole lot, so you can have bulk densities that are 100 times higher on this side of the diagram than on this side of the diagram. These are some models I computed about a decade ago from our expectation for our pure hydrogen-helium 4 billion-year-old planet at 10 AU versus one at 0.02 AU. We think gas giants form hot at large radii on the order of 2 Jupiter radii and then contract. Their interiors cool off as time goes on, so they contract. And so it was suggested that giant planets very close to their parent star should not be able to contract and cool off as easily, so that we expected some amount of inflated radii. But in reality, a lot of these planets are much larger than expected. And as I'll come back to in the last part of my talk, we can examine this population of inflated planets to try to understand what might be causing their radius inflation. So what we're trying to do then is, amongst this population that looks incredibly diverse, to try to understand any key physical processes that unify them, if at all. So one of the reasons I like this science these days is that we're kind of taking another look at simple models of giant planets, but as people were doing with Jupiter and Saturn 40 years ago, but with a much larger sample size. So this is a pie diagram made by my advisor, Bill Hubbard, in 1973. Looks very similar to the one I showed you 5 slides ago. Liquid molecular helium, liquid metallic helium, a small core in Jupiter. Morris Podolak and Al Cameron ran similar models in '74. They found that Jupiter had about 40 Earth masses of metals in its interior, which is actually pretty similar to what we get today. The number today is a little bit lower. But the basic idea of Jupiter being around 10% metals by mass has really stood with us. So relatively simple models that didn't have the details of the gravity field that we have today have really withstood the test of time. And we're kind of redoing this science now with a much larger sample size. And to me, I really enjoy that, being at these early days in exoplanet science. So this is a plot that gets shown sometimes when we think about hot Jupiters, which are these close-in gas giants. This is planet radius in Jupiter radii versus the flux incident upon the planet. This is like the solar constant. So Earth would be way over here. So these would be about 1,000 Kelvin planets. Over here, you'd be up at around 2,000 Kelvin planets. And if you plot planet radius versus flux, you can see that as you get to hotter and hotter planets, you tend to get larger and larger radii. There's a lot of scatter. This is also color-coded by mass. The expectation for a 1 Jupiter mass object at several billion years old, it would be this black curve here. And so you can see that this radius anomaly doesn't really exist for these cool planets. If you're below this curve, that's fine. That probably just means you have more metals in your interior, as I'll talk about in a minute. But this radius anomaly affects these planets to varying degrees. And there's a cutoff at around 2 times 10 to the 8, which is about 1,000 degrees, separating the planets that don't seem to have a radius anomaly with those that can have a radius anomaly. And so for the first part of my talk, I want to focus on these cooler objects over here. So one of the things I typically enjoy is making relatively simple models, but then trying to figure out what they tell us about planetary composition. So these are relatively simple models of the contraction of gas giant planets. So as they contract, their interiors cool off because they're reasonably degenerate. So a thermal evolution model of a gas giant planet, you can kind of think of it at early on, it's kind of like coming down a Hayashi track, and its interior heats up a little bit, but then it becomes fairly degenerate, so then more like a white dwarf. Its interior cools off as the planet contracts over time. And so if you have a solar composition object, this is about a half Jupiter mass at 0.1 AU from its parent star, it'll start around 1.6, 1.7 Jupiter radii and contract over time. Now, if you have a measured radius and estimated parent star age, what you can do in a very simple-minded way is think about if you replace 30 Earth masses of hydrogen and helium with 30 Earth masses of ice and rock, or 60 or 90, how that would affect the contraction of the planet over time. And so we're doing this within a Bayesian framework running several thousands of models per planet, but in terms of my mind, this is how I think we're trying to do it. There's a given planet, we have its known mass, radius, and age. We're trying to find the family of evolutionary histories that go through this box, essentially. And we can make diagrams like this. These are, for these cooler planets, there's a sample size of about 45 planets out here. So we're looking at these cooler objects out here. We can assess the amount of metals in Earth masses in their interior, given their mass, radius, and age. We actually don't know where the metals mostly are in the planet. So Jupiter, we think most of its metals is in the envelope, whereas Saturn, most of the metals are in the core. So we can treat that as an uncertainty. So we can put all the metals in the core, we can put all the metals in the envelope. The hybrid model is the first 10 Earth masses go in the core and everything else goes in the envelope. You can see it makes some difference, but not a significant difference. So for some planets like WASP-8, we can relatively well understand the metal enrichment. For some planets like HAT-6, there's a distribution that includes essentially the solar composition, or metal-free, along with this distribution. So each particular planet has a distribution of metals based on its mass, radius, and age, and the error bars associated with them. So then we can make a diagram that looks like this. This is the heavy element mass, the metal mass in its interior in Earth masses. This comes from the structure model itself versus planet mass. And so these curves would be 0% hydrogen and helium up to 99% hydrogen and helium. And so my phone is doing something. Not an Amber Alert, though. So what we have is some, I think, pretty reasonable evidence that all gas giants have on the order of 10 Earth masses of hydrogen, 10 Earth masses of ice and rock within them, which I think agrees well with the core accretion idea. But then as you go to larger and larger masses, you're accreting additional heavy elements as well. You're not just accreting hydrogen and helium, you're accreting additional amounts of metals. Jupiter and Saturn are shown here and here amongst this distribution. So they seem to fit in reasonably well compared to the sample. One of the things I think is quite interesting is as you go up to relatively high masses of 4, 5, 6 Jupiter masses, some of these objects are really accreting a lot of metal. It's not just 10 Earth masses with a little thrown in. It's something on the order of 100 Earth masses of solids being accumulated by these planets. So they really are obtaining a lot of material from their disk. These planet masses over here are on the order of 1,500 to 2,000 Earth masses. So
Are you assuming the inflation mechanism is not operating?
Yes. So these are these cool objects. So we're assuming the inflation mechanism is not operating. If there is some additional inflationary power that is actually there, then these would be lower limits, and you would need more metals then. It's a great question. I should have stressed that earlier.
So is this all close-in planets, or is it directly?
So these are all planets with a mass, radius. So they're all transiting planets. So they're all typically, these cooler ones are kind of 10 10 days and out. So I think the longest period is like HD 80606, that very long, which is like 100 days, I think. So they're typically on the order of 10 days.
Sorry, for
Yeah.
the planets around 1 Jupiter mass, those with 100 Earth mass of heavy elements, does this mean that the core is really heavy because the amount of solids in the envelope is going to be the same because it's whatever it is. So does this mean that the initial core was way heavier than Jupiter's?
I think it's more likely, personally, that perhaps they have a 10 or 20 Earth mass core and they've accumulated 70 Earth masses into their envelopes. But I think that's testable, right? So one of the things I'll come back to is if we can get spectra of the atmospheres of these planets, we could tell if their atmospheres are super enriched in metals, something like, I don't know what this would even be, 30, 40 times solar. That's, boy, sorry. I got 4 texts. I can't answer that. That was Enrico Ramirez Ruiz, or anyone who knows Enrico. He's our department chair, so sometimes there's lots to talk about.
And these were calculated with the same opacities. So you didn't assume that those ones that look like they could have more heavy elements and maybe more heavy elements in the core could have larger opacities. You didn't include that. You just said,
So we use the proper atmospheric boundary condition based on how cool the planet. We're interpolating a bunch of different atmospheric boundaries, but we have not recomputed the atmospheric boundary conditions for extremely metal-enriched atmospheres. If you did that, you would need even more metals, because you would further slow the cooling in the atmosphere. So that'd be another way in which these would be lower limits. It's another good question. Yeah.
So you predict that those really high heavy metal planets would be around metal-rich stars?
It turns out, we don't really see much evidence for metal-rich stars making metal-rich planets. So I'll come back to that in about 5 slides.
More metals in their atmosphere if the gas itself in the disk was not more metal-rich than stuff.
That's a great question. I don't have answers for all these things. I mean, I think that's an essential question. If these planets are extremely metal enriched, but they're typically around stars that aren't that metal enriched, I'm not sure what that means.
Sounds like it's evidence for migration.
Or being able to accumulate metals from a wide feeding zone. Yeah. So what we did do is calculate Z star from the star. That's just based on the star's iron abundance, compared to Z planet, the planet's metallicity from the structure model. And we can make this metal enrichment, Z planet over Z star. If they all had their parent star, they'd sit down here at the 1 line. And so you can see Saturn and Jupiter amongst what I call their cousin planets. And so there is a trend we see in the solar system. There's a clear slope here. There's a tremendous amount of diversity, right? So you can have Saturns that are more metal poor compared to actual Saturn, objects that are much more metal rich compared to our Saturn. So again, this is from a structure model, but we actually, not really in our era, I would say, but in the James Webb era, we can start to pinpoint these particular planets to see if this is borne out in terms of their atmospheric abundances as well. So this is a paper by Christophe Mordicini's group. They do planetary population synthesis, where they're modeling several thousand planets in a wide variety of planetary systems, looking at different disk masses, disk lifetimes, parent star masses, treatments of opacity. I just want to mention that data like this has been useful. This is an older compilation with we did about 7 years ago now, where we had a sample size of 11. Now we're up to almost 50. But the basic idea was of the Mordicini paper was tuning some of the models. So as this was pointed out before, a model where they had no migration led to planet metallicities that were not high enough, whereas a model where they had some amount of migration led to higher metallicities for their planets and a better fit to this previous compilation. So planetary population synthesis is still in its infancy. A lot of shortcuts have to be made to run several thousand structure and formation models. But I do think this data is going to be useful in the future. So some of the things we're thinking about right now is thinking more about what the stars are like. So we've been collaborating with Johanna Teskey, who's a Hubble Fellow at Carnegie, and she's an expert in stellar abundance analyses. And so we've been trying to think about what, not just iron, but other planet-forming metals. So things like silicon, magnesium, nickel, carbon, and oxygen. So out of these 47 cool planets I mentioned, about 25 of them are around bright enough stars that we can get a very high signal-to-noise spectrum to pull out these abundances. So we did that with Keck High-Res, or Johanna did, and Magellan Mike in the northern hemisphere and the southern hemisphere. And so we want to compare these planet metal mass fractions, these heavy metal abundances, versus these non-iron abundances. So this is work that we're writing up right now. So what we've done in this plot here is what we had before. This is Z planet divided by Z star. This is the true Z star. This is not just based on iron. This is based on the abundances of oxygen, carbon, and the other metals. And so we can fit for this slope, and it's basically the same. It's very, very similar to what we had before. This is just the metal enrichment compared to planet mass. The correlation looks essentially the same as what we had before when we just had the iron abundance. But more interestingly, we can look at this residual metal. So residual metal is excess metal compared to the fit. So there's the fit. And so excess residual metal, if you're above, you have more metal than the fit. And if you're below, you have less metal than the fit. And we can look at this as a function of the parent star's metallicity. And you can see it's relatively flat. So it could have some slope, but it looks like a slope of 1 is not favored. So a slope of 1 would mean there's a direct relationship between parent stars being the more metal-rich stars making the more metal-rich planets. That's what a slope of 1 would indicate. And so there's certainly a lot of room on this side of the diagram for metal-rich parent stars to make metal-rich planets, but it doesn't seem to be the dominant effect. So that goes against my expectations, certainly. So it looks like there is some positive slope, but it doesn't have to be a positive slope. It could be quite flat. One of the things that has popped out, though, that I'm still mulling over, is if we look at this residual metal compared to what we're calling the volatiles to refractories ratio. So the volatiles are the carbon and oxygen. The refractories are the iron, silicon, magnesium, and nickel. And what we are finding is that the parent stars that have the highest volatile to refractory ratio compared to the sun are the systems that have the highest residual metals. So the systems that have the most volatiles compared to refractories are ending up with the planets that have the most metal-rich composition. So to the extent I have thought about this, because we made this plot about a week ago, it suggests to me something having to do with formation at or near an ice line, where you probably have a lot of metals near there, and also probably are enriching the gas in those metals as well as planetesimals drift across that ice line. So I don't know if that's the right answer or not, but I found this to be pretty curious. But that's a new result that we're still mulling over, which we can chat about at coffee afterwards. Or cookies, right? Yeah. I mentioned a few times about trying to test this with atmospheric abundances. And so this is what we know for Jupiter and Saturn and Uranus and Neptune. So this is the abundance relative to the protosolar abundance ratio for a bunch of different elements. So for Jupiter, we have about a 3 times solar. For Saturn, we have some spectra that indicate around 10 times solar. For Uranus and Neptune, these planets are extremely cold. They're so cold that only methane is left in the atmosphere. Everything else is either transparent or frozen out of the atmosphere so that we can't see it anymore because they're about 50 Kelvin. But they're on the order of very metal enriched. Uranus and Neptune are about 90 times solar in carbon, extremely metal enriched. And so we can try to think about connecting atmospheric abundances to the structure models. So as I'm sure you're aware, in transiting planets, the planet can pass directly in front of its parent star. You can look for molecules in the planet's atmosphere, look for absorption features in the transmission spectrum. We can also look at secondary eclipse when the planet passes behind its parent star and then reappears. You can take a spectrum of that as a function of time to look for molecules like water, CO, CO2, and methane. This is a paper that I worked on with Christophe Mortacini about 5 years ago, looking at Christophe's core accretion population synthesis models. And this is the expected metallicity of the hydrogen-helium envelope. So again, the sun would be down here at 1.5% as a function of planet mass. And so from the population synthesis, Jupiter would be down here at, the average Jupiter would be a little bit higher than the 3 times solar that Jupiter would have, Saturn, Uranus, and Neptune. The fact that these all turn over is a story for another day. That's the effect is planetesimals ramming through a very thin atmosphere and just smashing down on top of the core. But as you go to lower and lower planet masses, there's relatively less envelope so that you get these higher enrichment in metals. And so we'd like to be able to test whether or not this is borne out in the atmospheres of transiting planets, not just in their structure. And so people have started to do this. This is this atmospheric metallicity. This is from transiting planet atmospheres, from their emission spectrum or their transmission spectrum. This is this metallicity versus mass. And so you can plot Uranus, Neptune, Jupiter, and Saturn on this plot. The trouble with exoplanet atmospheres is that often the error bars are quite large in the abundance analysis, mostly because we're using Hubble Space Telescope Wide Field Camera 3, and that typically only has a very small wavelength range of about 1.1 to 1.7 micron. So you often get pretty large error bars. But the general trend is, well, the trend, there's a clear solar system trend. It's not obvious there's a trend in exoplanetary systems. And maybe there will be and maybe there won't. So these are some Neptune mass planets. There's WASP-43, which is about 2 Jupiter masses. We can compare this trend to what we've seen. And this is our trend from the structure models. This is the possible trend from the exoplanetary atmospheres. I want to point out is that these are very complementary ways of studying the same objects. But we also can provide a check on some of these as well. So WASP-39, there was a paper by Wakeford et al. That suggested that this Saturn mass planet might be around 150 times solar in its atmospheric metallicity, well above actual Saturn. And the data looked like this. This is the transit depth in planet radius over our star. So it blocks out about 1.5% of its parent star's light. And so this is a transmission spectrum. This is wavelength. So any absorption feature goes up on a diagram like this because the atmosphere is absorbing more of the parent star's light. So there's a water bump here, maybe a water bump there, and another water bump there. And this is perhaps due to some Rayleigh scattering, but it's pretty noisy. But they found something like 150 times solar in terms of the oxygen abundance that you see in water. And so what we did was we looked at the atmospheric metallicity compared to the structure model. And so the structure model comes from the planet's mass, radius, and age, just like we talked about before, putting all the metals into the interior in the envelope. And we get something that's on the order of about 20 times solar, whereas the atmospheric model was something like 150 times solar. So there's lots of ways to interpret this. The way I interpret it is that exoplanet atmosphere spectroscopy is still in its infancy, and that we can use structure models to inform what are realistic atmospheric abundances given the interior structure. Another way to interpret this might be that there is a lot of metal in the planet's atmosphere. Perhaps they got dumped on by the accretion of nearby planetesimals, such that the atmospheric enrichment differs from that of the hydrogen-helium envelope as a whole. That would also be extremely interesting. we can't say for right now. But it does suggest that structure and atmospheres are going to be interesting when thinking about them in tandem as we go forward. As we go to the James Webb era, we'll be able to get error bars on the spectrum typically 10 times smaller over a wavelength range from about 0.6 out to 5 microns and beyond. So we'll have much more robust atmospheric assessments.
Jonathan?
Yeah.
Is it obvious that there is no way of segregating the metals going through this very deep radiative zone connecting to the convective zone? Because you're making the assumption you mix uniformly everywhere.
Yeah, so we're making the assumption, yeah, so my expectation is that the deep atmosphere in all the interiors is convective, and so that's well mixed. What Kristen's mentioning is that the actual atmosphere we see is radiative, and that radiative zone probably goes down to something like, depending on the planet, 10 to 100 or even a few hundred bars. And the question of whether or not you stay well mixed in that region, I think, hasn't probably been definitively answered. It seems like in the visible atmosphere, there seems to be a lot of circulation, and circulation models have suggested that that part of the atmosphere gets reasonably well mixed. But between a bar and 100 bars, it might be a little more quiescent. So I know people used to think that it might go the opposite way, that the atmosphere might be very depleted in metals due to it just sedimenting out of the radiative zone. I haven't seen that advocated very strongly lately, but that would be the opposite of that. I think it's interesting.
So for the blue, which is coming from the structure,
Yeah.
what do you assume for metallicity in the atmosphere? Like solar metallicity? Is that what you assume?
The thermal evolution of the planet, the atmosphere grid, assumes a solar metallicity. Yeah. So
Everything in the core.
no. The structure model itself is putting everything into the envelope. But there's an inconsistency between the metallicity of the whole envelope and the upper boundary condition that we're using. That's a good point.
But you do have also a core, a rock.
So for this one, we tried to maximize the metallicity of the envelope, so we didn't put in a core. If we put in a core, this would only move to the left.
So that's a fully core-eroded.
That's right. Yeah. Just as a test, basically. You know, I should. Oh, sorry. Yeah.
To go back to the observation,
Yeah.
reason they think such a high metallicity is because of the scale line being too small, or is it actually just a spectral tissue being very, very strong?
I don't remember the detail. That's a good point. Sometimes you can get high metallicities because it actually leads to a mean molecular weight that squashes the atmosphere and makes the features smaller.
Then you want to tune up the
Right.
metallicity.
I don't remember. I'm sure there's a correlation diagram in the paper that describes that. Yeah. I should mention, I've been terribly remiss at not mentioning my graduate student, Daniel Thorngren. So Daniel's a fifth-year graduate student in physics at UC Santa Cruz. And so he has been doing a lot of pioneering work at the interface of planetary interior structure and Bayesian statistics. And so it's been a really nice partnership to work with Daniel in that we kind of often see problems in a very, not the same way. And so it's been a fun way to think about how we're able to pull out a lot of this planetary physics by coming at a meeting of the minds in terms of how we assemble the models. So Daniel is going to be doing an internship this summer at Amazon. And at the end of that internship, he's going to decide if he wants to go into planets or go to Silicon Valley. So we'll see. I think he would be phenomenal at either, and I hope he picks whatever makes him happy. So, okay. So, giant planets as a class are enriched in metals. They're enriched compared to the sun. They're enriched compared to their parent stars. There's apparently a very wide spread in the enrichment at a given mass. This may indicate the role of different formation locations, may indicate a role for stochastic processes. The enrichment's a strong inverse function of mass, but even the superjupiters are enriched. And the structure modeling is complementary to atmosphere modeling, can sometimes serve as a check And it's also fundamentally an easier calculation than trying to actually interpret spectra. So we've had a lot of great questions, and I stuffed in all this new stuff without taking anything out. So I'm going to try to get this last bit done a little quickly, but we'll see how it goes. So this is a very similar plot. This is the radius anomaly, transit radius versus wavelength. So this is just updated. More planets. Again, there's this cutoff at around 1,000 degrees, 2 times 10 to the 8th. So the first half of the talk was focusing, or half. The first part of the talk was focused on the cool objects. We can also look at the hotter objects as well. So we're going to focus on these objects that have much larger radii. And so there's been a lot of investigations about why these planets have large radii. So this has been an active area for almost 20 years, why the hot Jupiters have such large radii. You're not supposed to take this all in, but you're supposed to appreciate that a lot of people have been thinking about it. Most theories posit some sort of physical mechanism that transmits something on the order of 1% of the parent star's energy that's absorbed, which is absorbed around here. Posit some mechanism to get that energy down deeper into the atmosphere to 10 to 100 bars. So these are atmospheric pressure temperature profiles calculated with a very hot interior, which would be a large radius, or a colder interior, which would be a smaller radius. So up here, this is all absorbed and re-radiated stellar light. It doesn't really care what the interior is doing. But the idea would be to transmit some fraction of the parent star's energy through some dynamical mechanism deeper into the atmosphere, such that you could actually add this energy into the deep interior and get a larger planet radius. So one of the problems about trying to quantify this ballpark 1% is that we typically don't know the metal enrichment of the planet. So you could imagine these are 3 families of curves. This is a pure hydrogen helium planet. These are 3 families. These are another 3 families, the same model with about 30 Earth masses of metals in the interior. So pure hydrogen helium and then metals. And this is no additional power, 1% and 2%. And you could see that if you just had a mass and radius and age over here, without knowing the metallicity of the planet, it's hard to quantify the amount of power you would need to explain its radius. So what we did is we assumed that the mass metallicity relation we derived in the first half of the talk for the cooler 50 planets also applies to the hot 250 planets, which I think is not a horrible assumption because we're talking about planets at 10 days versus planets at 3 days. So we're assuming they're similar, but that's an assumption. So what we have then is for a given planet, we have its mass with error bar. We then derive the z of the planet based on the mass metallicity relation. We can then infer what this efficiency epsilon, which as I said is something like 1%, we can infer what that is. And then there's also an age uncertainty, typically a very wide age error bar. But we can do that for so you can think of this as a compositional prior. We have these 250 planets. We're assigning them a metallicity based on their mass from our previous work, and then trying to infer what this epsilon, this 1% number, needs to be to explain the radius we see today. And so people have thought about this before, but typically they haven't compared to observations in an extremely quantitative way. So this is a recent paper by Tremblay et al. Positing yet another mechanism for inflating hot Jupiters. But all they really did is they said, well, this is our normal model. This is our inflated model. This seems to work. And so it's not a very quantitative way of comparing their model in red to the data in blue. So what we aim to do is building up a more quantitative way of comparing a model to data. And so we did this for the 300 planets. We get a diagram like this, which is the key result of this last part of the talk. So this heating efficiency, so this percentage of the parent star's flux, the absorbed parent star's flux that we're assuming is going into the convective part of the atmosphere down below. So this is this 1% number as a function of the planetary temperature. And so we tested a variety of different models. This is a power law model in red. This is a logistic model in yellow. And we did the Gaussian process model where we didn't assume a functional form, and that was in black. And so black is the most robust model, as I'll show in a minute, which shows that as you go to the cooler planets, this goes down to essentially 0. As you go up, there's a maximum at around 15 or 1600 degrees, and then it goes back down. This is, again, as a fraction of the absorbed energy. It goes back down. So we can look at what this means for the radii of the planets. So if this is 3 different models. This is no inflation, then the yellow model, and then the Gaussian. So this is yellow and the Gaussian. So if there's no inflation mechanism, it's this tremendous radius anomaly. All the planets are too large. The yellow model over here gives us, these are just the hottest planets over here. What the yellow model over here finds is that if you assume it flattens out and stays at around 1%, what that gives you is that all these planets down here are too large. These are all off the bottom. They're too large compared to the dashed curve. Only for the Gaussian model, where this efficiency goes back down again, do you then get the best fit to the data, indicating there's some scatter, of course, but there's no residual offsets as a function of temperature like there is for these guys over here. So what you get then is a functional form for this efficiency as a function of planetary temperature, which is a new result that we haven't had before. And it looks like a Gaussian. And so to my knowledge, there's only been one of the many ideas for what inflates hot Jupiters that suggested a quasi-Gaussian-like shape. So it was suggested by Batigan and Stevenson, and also work by Perna and Kristen around the same time, that there can be ohmic dissipation in the atmosphere. And so this arises because these hot Jupiters we know have a flow from day to night. That flow is a circulation in the atmosphere. It's a hot atmosphere, so you actually get thermal ionization on these ions. So you have a flow of ions through the atmosphere from day to night. The planet has its own magnetic field out of its interior generated by its dynamo. And so what you end up driving then is a current that gets driven down into the planet's atmosphere and is dissipated ohmically in the deep atmosphere. Where in the deep atmosphere is still a matter of discussion, and it matters a lot. If it's at 1 bar, it's not going to inflate the radius very much. If it's tens of bars, it can inflate the radius a fair amount. But this general shape comes from, as you get a relatively cold planet, there's almost no ionization, so there's almost no of this current from the wind. As you get to very, very high temperatures, there's a lot of ionization, and that ionization can actually stall the flow. It creates too much drag. And so there can be a sweet spot. It's not exactly clear where the sweet spot is, but a few authors have suggested it's around 1600 degrees, where in the sweet spot where you have still a relatively fast flow, but a fair amount of ionization. And Daniel produced this plot, and then I went home that night, and I went to a movie night at my boys' school, and it was the movie Trolls, the Trolls movie. And I was not particularly excited about the Trolls movie, so I sat on the side, I pulled out my laptop, and I kept thinking about this curve. Where had I seen this before? I pulled up any paper I could remember about ohmic dissipation or anything, and I remembered that I was the referee for Kristen's paper in 2012, which he didn't know until today. And And I thought, oh, that is kind of like what we saw. Actually, these numbers are pretty high. This is more like 10%. So we'd be down here. But in terms of a quasi-functional form, it agrees reasonably well. And so I would say that it's not proof that this is the answer, but if it isn't the answer, we at least now have a functional form for the intrinsic power that we can compare with any new theories that arise.
Precisely define TE for us.
Oh, I'm sorry. That is the equilibrium temperature. That is the.
Effective temperature.
It is because there's so little flux coming out of the interior. That's the temperature you would have in the absence of any flux from the interior.
The upper radiated layer, that's the temperature that it tends to.
Yeah. It's kind of like the photospheric temperature, more or less. Yeah. So, okay, I blew through that fast, so we finished on time. Okay. So, One of the things I think about is what sorts of questions we can actually ask and answer. And so there's lots of planetary science questions that we can answer about exoplanets because the data set we have is not detailed enough. But we have a much larger data set. And so we can answer questions that you couldn't possibly answer in the solar system because we have a much larger sample of objects to look at. So population-wide, the heavy element enrichment is common to all gas giants, and it's a strong inverse function of planet mass. We can test hot Jupiter radius inflation in a new way now that we have hundreds of objects, not just a handful. I certainly remember when I was a postdoc and we had like the 5th transiting planet, and I kind of thought that transits were on their way out. That seemed like that was just so many. And that there's emerging correlations with stellar abundances that I think is going to be really interesting, and that could point towards planet formation, moving things into new directions. That's where I'm going to be spending some of my time in the future. So I'm happy to take any questions. Thanks.
And it's great to see the peak, but don't you think also seeing the effect rise at about 1200K is sort of also a prediction of the model, or do you, I mean, by itself, maybe you can go further model that would do that?
So yeah, I think that's true, right? So yeah, a prediction so a prediction of this model is that there is a rise as you start to get ionization. So other models, I've thought about this a bit. So I think other models that don't involve ohmic dissipation to inflate the radius could also have this, because the ohmic dissipation could be stalling the flow even if it's not inflating the radius, right? So I think other theories could probably get something like this just because the atmosphere is ionized. So you might expect something like that. But I personally do think the fact that it tails off at low temperatures, that to me is very suggestive, because if it was some other dynamical mechanism that just had to do with the wind speed and that was it, you would have to have the wind speeds really go down very sharply, which there's no evidence for that in our own solar system. I mean, Neptune has the fastest winds. So that to me is, yeah. So not just the peak, but I think the shape.
It's just a coincidence that the turnover as well silicates sublimate?
I think it's just a coincidence. I think, yeah.
Jonathan, can you show back your plot of the volatiles over the refractory?
Yeah, sure.
So these were, you had a test, you actually looked at the individual stars, is that correct?
Yeah, so for these we have the 6 abundances of all the stars.
Of all those stars, and then can she get something like other volatiles that are a lot less, but will not have these processes like potassium, for example, alkaline metals that are volatile? You would expect them perhaps to, be more subjected to processes that can deplete it, but not be so abundant, and would not have a relationship whatsoever with the snow line that you can.
Okay, that's a great. Yeah, I don't see why not. So, okay, that's a really interesting thought. So, thinking about things that are volatile, but maybe that are not involved with the snow line and aren't dominating the total metal abundance either.
We can talk
Yeah.
about why
Okay. All right. Yeah, that's interesting. Okay.
Can you explain again why ohmic heating becomes inefficient at high temperatures?
Yeah. Anyone else can throw it in. And my impression is that the reason why it becomes less efficient at high temperatures is that your typical wind speeds are relatively constant across here. But as the ionization fraction becomes so large, the fact that your wind is ionized and the planet has its own magnetic field, that starts to that makes a drag force on the wind. So the wind actually physically slows down. And so the wind speeds are decreasing as you go from hot to very hot. And so
Is there any evidence of that from day and night temperatures?
there is a relation that the hottest of the hot Jupiters have the smallest offset in their hot spot. Their warmest spot is closest to high noon. And as you go to cooler hot Jupiters, their hot spot is actually shifted downstream, indicating that there is a faster flow relative to other time scales. So it's suggestive, yeah.
Another point would be when the ionization fraction is of all the units.
No, it's much less than
It's much.
So basically, the energy for home emitting in this scenario comes from the kinetic energy of the wind, right? So you can tap a percent of it, and you don't slow down the wind, and you start developing energy. But after a while, you start feeling the drag. So I think that's what he said. The drag starts being important, and it shows up.
Yeah. So here it's. Well, sorry, I should have mentioned this. The ions come from the alkali metals, and so their abundance is 10 to the minus 5, something like that. So, yeah, it doesn't take a lot.
It's the same thing that happens in accretion disks. In the planet forming disks, they are ionized and MHD within 15K or whatever.
Okay.
And they are the magnetic radiation.
Yeah. Right. Okay.
So if you use the model from the planets that were below 1,000 Kelvin,
Mm-hmm.
but that line of 1,000 Kelvin is subject to a little bit of tuning because the models are not perfect.
Sure.
So if you instead took something like 2,000 Kelvin, does that shift this peak at all?
So you're saying if we did if we used a slightly different compositional prior based on a different sample size and applied that, I really doubt it. So.
It doesn't look like immediately prior results already kind of this plot.
Yeah, I mean, yes. That in after the fact, you can note that that it turns out, and we actually didn't notice this till after the fact, and I don't think anybody else. I could be wrong. That the most inflated planets are around 1,600 degrees, and at 2,500, there's inflated, but they're not.
I think in my paper I mentioned an earlier plot like this, where
Okay.
but there were very few points.
Yeah.
And yeah, so I think it was open to interpretation.
Okay.
And it's a bit clearer on this plot.
Yeah.
But now you get,
Right.
now you, hindsight, you figure out what it is.
Right.
I have a question.
Yeah.
So you said we can measure the metallicity of our Saturn to be 7 to 10 times solar.
Uh-huh.
So if we know Saturn's metallicity to only within a factor of, let's say, a fraction of 30%,
Mm-hmm.
how do we know better than this for the actual planets using GWST? And in other words, is 30% uncertainty already good enough?
If we had a 30% error bar in a atmospheric abundance measurement,
And can we achieve that for extrasolar planets?
I doubt we'll get an error bar that small for an exoplanet atmosphere, 30% error bar. People have simulated James Webb data and then retrieved on it, and it's more typical to get a factor of 2 or 3. So, so that suggests you would like to have a very large sample of planets if your typical error bar is going to be relatively large. And so a trend might not emerge if you only have spectra for a couple dozen planets. So there's this European mission called Ariel that recently got approved. It's going to launch in about 2028 or something. And that's going to be focused on the spectra of transiting planets, both in emission and secondary eclipse. And one of the science cases is to get high quality spectra for something like 500 to 1,000 planets. Because it's a dedicated space telescope just for transiting planets where, given time constraints, it's possible James Webb might only do 50? I didn't really make that number up. I think people generally think that might be the number. So.
All right, so we have cookies upstairs, and we are going to take Jonathan from the dinner, so you can join. There we go. And let's thank Jonathan again.
All right, thanks.